we'll get
Anyway,
there.
we are.
Okay, let's go for it.
Well, yeah. So, Emery, so Alan, this has been a work in progress to get us together on the schedule to be able to have this conversation. But I'm super excited. The work you've been doing, looking at the Irish Sea and Irish offshore wind, is really quite interesting. So why don't you give a quick introduction to who you are, and then an introduction to the project itself, and then I think we'll just let you go through your slides, and then just have a kind of a casual Q&A.
Yeah. Okay, thanks, Marcus. Yeah, my name's Alan Henry. I'm originally a mechanical engineer and have a PhD from Queen's University in Belfast in wave energy. I was a senior research engineer with Aquamarine Power, working on the Oyster wave energy converter for a number of years. And since then, I've been running my own consultancy business, which is Rockall Research. And we're kind of a specialist, or a small team of specialists in the area of the general area of marine renewable energy. So anything from hydrodynamics, simulations, performance predictions, engineering design, that kind of stuff. But more recently, we've moved into the area of looking at installation, operations, and maintenance of marine renewables. So I'm going to talk to you a little bit about that today. I'm actually going to talk about two projects, and it's going to be melded into one. So hopefully it makes itself clear. The recent project that we're actually working on at the moment is called DFOT. So that's de-risking Ireland's floating offshore wind targets. So diving straight in. So floating offshore wind in Ireland. It's a massive opportunity for Ireland. Ireland sits in the Northeast Atlantic, and we really do have a very fine wind resource. And we do also have a very large sea area, which is, I think it's 8 or 9 times our land area. So there's a huge opportunity for Ireland to generate a lot of clean energy in our seas. And basically, in terms of Ireland, those that are familiar with it will know that we're probably not blessed with a solar resource. We do have a wave resource. We don't have a huge amount of tidal. So in terms of renewable energy, wind is our thing. That's the way we're going to decarbonize, and that's the way we're going to kind of secure our energy supply. And much of that resource, of course, is offshore. We do have targets in government to develop some 37 gigawatts of offshore wind by 2050, and that's kind of split. In the Irish Sea on the east coast of Ireland, we have kind of shallow sandbanks, which are they're pretty good for fixed wind. But obviously on the west coast and the south coast, the water depths drop off quite quickly into 50, 80 meters. So that's where we'll see a lot of floating offshore wind. And so I would say floating offshore wind makes up the vast majority of that 37 gigawatts. It's probably the order of 25 to 30 gigawatts of floating offshore wind by 2050. And I suppose the more optimistic amongst us would suggest that why stop there? And some have suggested that figure could be over 70 gigawatts in the future, and that with the right grid connections to Europe, we could be a net exporter of clean renewable energy. The risks associated with developing floating offshore wind in Ireland. I mean, the first thing to point out is, these turbines are very large, and very quickly the Eiffel Tower seems to be becoming the unit of measure for a floating offshore wind turbine. I've put in a 15 megawatt turbine now, and that's starting to feel a little bit old hat and small as people start talking about 18 megawatts and even 20 megawatts. But just to put that in perspective, that's by far the biggest structure in Ireland. Our tallest buildings we don't really have buildings that are any bigger than 15 stories. So our tallest structures are about 200 meters, and they'd be power station towers. And these turbines are over 300 meters tall at this stage. So look, we don't really have suitable port facilities for floating offshore wind at this point. We don't really have a history of a significant maritime industry, I would say. I mean, we do have, ferries and cruising and that kind of stuff, but we're not we weren't a place where there was shipbuilding or anything like that. So we don't have a history of that kind of thing. We don't really have a workforce, the equipment and the vessels. There's other issues around, grid connection, which wouldn't be unique to Ireland, but certainly the west coast of Ireland. Our population centre is in Dublin. Over a third of people live there. So as you go further west, where our wind resource is, the grid connection gets weaker and weaker. It'll be no secret that there's planning and consenting issues within Ireland, and last but not least, the weather in Ireland. Although we have a very fine wind resource, that also brings its challenges as well, which will be the kind of one of the focuses of this study. So in terms of risk mitigation, I think the first thing in the problem solving handbook is actually to define the problem first of all, and I think that's what we're trying to do. So really what we're trying to do is do some research to quantify the needs of the industry and to use that to inform policy. So the outputs of our study should be taken forward into developing a national port development strategy. Also coordination of ports. It should affect our support schemes for renewable energy as well, and it could also aid in marine spatial planning. And it's worth saying that we're not, we're not necessarily bereft of anything in Ireland. We have plenty of things coming through government at the moment. We've set up our own MARA, so we're regulating the marine area and stuff like that. So we are progressing, but we still need an overall strategy to de-risk the development of floating offshore wind in Ireland. And this study is part of that, providing that solution. So who is in DFOT? And DFOT is led by myself and my team in Rockall Research. As I said, we're a specialist consultancy. Wave Venture, also rich history in marine renewable energy, and they're also the developer of the software, the Tempest software that I'll be presenting on here too. MMCC Port Marine are a specialist consultancy in Ireland who work in the maritime consultancy. So anything to do with ports and vessels, Michael McCarthy is your man in Ireland. He knows every nook and cranny in the coast, having captained ships in and out of them. And lastly, we have Wind Energy Ireland as a partner, and they help us with stakeholder engagement and dissemination. So they've been great to work with. And the project is funded by SEAI, which is the Sustainable Energy Authority of Ireland, which essentially funds our transition to decarbonise. So just a bit of kind of rolling back. So we did have another project in 21-22, which was called SIMRE, which was support infrastructure for marine renewables in Ireland. That project's finished, and I'm going to actually talk about some of the results from that later on. I don't want to make this too confusing, but DFOT is a follow-on to SIMRE. So there's a kind of a seamless transition that I'll talk about. So essentially, SIMRE was kind of DFOT light, if you like. When we kind of drew up the project and applied for it, the just after that, the issue of the lack of port infrastructure in Ireland really blew up, and it became perhaps a bigger problem than we had prescribed in our application. So anyway, the focus of SIMRE was really just looking at port infrastructure. We were building up our kind of modelling capabilities. We looked at other stuff like the weather restrictions in Ireland. We focused a lot on assembly and installation rates. So really, the first start of the project, like how do we get these units put together and out of the port and out to the farm, and that led on to vessel requirements in terms of how many vessels were needed. And we also focused quite a bit on wet storage. I'll talk a little bit about wet storage later on, so I won't ruin that just now. And so the report is actually available on SEI's website. It's kind of a summary report from the project, so that's available. You can search for SIMRE if you go to the SEI website. So the difference between SIMRE to DFOT, as I said, it's a follow-on project. It's longer, it's 2 years with a larger scope, and we're moved away from that focus on ports to de-risking floating offshore wind in general, and more detailed simulations at wind farm and also at national level. And then, as I said, the addition of Wind Energy Ireland as a partner. So the objectives of the current project is to identify the key constraints and their impact on floating offshore wind development in Ireland. And then the core of that is not to keep that to ourselves, but to disseminate that widely and get our recommendations into policy. So the approach, and this is kind of the core thing, we kind of see this as a novel approach that we're taking, where essentially what we're doing is we actually simulate the rollout of floating offshore wind, and it's kind of a time frame from 2030 out to 2050 when we've installed, some 30 gigawatts of floating offshore wind. And by doing these kind of simulations, what we end up doing is creating a kind of an evidence base results, which can be used to de-risk flow in general in several ways, which I'll talk about. But just to put you in perspective, what we're talking about here is that we model the life cycle of every floating offshore wind turbine in not just a farm, but in clusters of farms and at national level. And that's every step of the way from it being assembled in the port, then it, at the quayside, and then it's moved from quayside into the wet storage area. So for those that don't know, wet storage is a term used to describe a place where floating offshore wind turbines, or even parts of the floating wind turbine, like the base, can be held, which are neither at the wind farm or at the quayside. And the idea here is that if you assemble a floating offshore wind turbine, but you don't have the appropriate weather to install it in the farm, you need to get it away from the quayside so that you can keep that assembly line going. And we've played with the rates of assembly of these units. So maybe we'd say that you could put together a one unit in 7 to 10 days, and you could maybe be doing two of them in parallel. Well, then you're producing several every month, and in the winter months you don't have the weather windows to actually install them at the farm, so you end up producing lots of these units. So you need to store them somewhere. So that's some kind of a sheltered bay or somewhere inside the harbour that isn't taking up space and isn't holding up your assembly line. The other option is that you down tools waiting for weather every time you fill up your quayside storage. Anyway, so that's the process, and then the unit goes out to the wind farm, and we even model the failures. So we look at the maintenance. So that's plan schedule maintenance, and also fixing things that are broken as well, and ultimately the decommissioning. And of course, by doing this study, we end up being able to create insights. We end up, if you think of, for example, vessels, we get to see how busy these vessels are going to be, how often they're used, what time of year they're used most. And worth saying that we've got a wind and wave hindcast resource in there as well. So essentially, we're modeling the whole 25 years, in a time stepping method. So the focus areas for us, what we see, the risks that we've identified with some stakeholders as well, is that idea of what, in an Irish context, what is the port and wet storage capacity that we need to make this happen? What vessels do we need, and what does the workforce look like? Who do we need to upskill and train, and how many of them do we need? There's also some nice stuff around the installation rates. So again, I've mentioned weather restricting how fast you can install a farm, but this has knock-on effects to the support scheme, where oftentimes there is a limit. I mean, you can't installing a 1 gigawatt farm in 5 years is probably not going to be a bankable project. So there is limitations there that need to be looked at. Obviously, I've talked about the weather restrictions on installations, operations, and maintenance. And then there's some knock-on stuff, like obviously if you're a project developer, you're interested in farm availability and the sensitivity of various parameters on your LCOE. So again, that's just making a project that's bankable. So with our simulations, we tend to focus on those areas, but we're always talking to stakeholders as well to find out what other risks they're interested in looking at. So digging into the software itself. So the software is, as I said, created by or developed by Wave Venture. It's called Tempest. So the acronym, quite a nice acronym, Techno-Economic Marine Planning and Energy Simulation Tool. It does a lot. It has several modules. I guess, you know, it can be used to do, you know, maybe for various stakeholders can use it, I guess, but what you would use it for is design, planning, optimize, and ultimately commercialize floating wind. I've written floating wind there, but this software can be used for all marine renewables as I see it. There's just different inputs depending on what they are, and potentially could be used for land-based things as well. And certain modules would be suitable too. So the basic, you know, at a high level, you know, there's a resource data module where you put in your wind and your wave and your tides, currents. You can even put in tidal range. So all that mid-ocean stuff is in there. And then you input various parameters describing, you know, each operations, the vessels, the speed of them, yeah, what wave heights or what conditions they can work in or can't, and ultimately you end up with being able to look at installations, operations, and maintenance over the life cycle of a project, and also look at the energy productivity as well. That knocks on to the finance module, because everything, of course, everything has a cost, whether it's capex, opex, etc., devex. It's all in there, and so you get to see. You know, it's quite a. I personally probably haven't gone this far with it, but you get to see when you know what your rate of return is and what your expenditure rates are, and when you start to break even with the project. And there's nice stuff around uncertainty, so you can put uncertainty on various parameters, which gives you that kind of range of values, so you've got more confidence in your results. So that's it. So just without kind of completely kind of bamboozling you with what it looks like, again, you know, it helps to answer various questions that a developer or any stakeholder might have. So again, you know, can you install your farm in a certain period of time? You know, in terms of maintenance, are you looking at, you know, towing each unit back to port? Or are you going to try and tackle offshore maintenance? So you can come up with hypothetical scenarios and start to understand the implications on that on, I don't know, availability, you know, cost being a big one, etc. And ultimately, is it a bankable project? So it is a kind of a, you know, written there, it's a kind of a holistic approach to modeling a floating offshore wind farm. It tries to take in as much as it can. It models each discrete event, and it allows you to vary things, you know, quite easily. So you create these kind of studies where you can have multi-parameter studies, and you know, you can play with things like, you know, what yeah, what, let's say the limitation on connecting a unit to its moorings or its electrical connection, so you can change the wave height that's allowable in, and then you get some nice results around yeah, how that affects yeah, LCOE or availability, etc. So just the next set of slides is kind of just a simple case study. So I'm just kind of going to give you a very rough look at the kind of things we can do. It's worth saying that these numbers are backed by a whole load of assumptions, and I don't want anyone to run away with these numbers and say, Alan said this is the LCOE of a project. So these is just an example. So we've got a 1 gigawatt farm. You know, we've 67 15 megawatt turbines. We just put in a 20-year turbine life, and we're down in the south coast of Ireland. So we're off, you know, the coast of Cork here, and I just put those rings just represent the distance to different ports, which will become apparent later, because we're looking at the distance from the farm to the port. We're going to look at fleet size, the energy production, and some LCOE and finance. So again, looking at those risk areas that we identified, this example, it looks at the parameter, which is the distance from the farm to the port. So we've got two distances, 100 kilometers and 250 kilometers. So top left, we're kind of showing that, you know, the blue line is the 100-kilometer port, and it takes us 3 years to install the 67 turbines. If we're further away, 250 kilometers, we're in the region of 4 years. I guess maybe even a little bit more than 4 years. Top right, same kind of thing. The impact of distance from port to farm. 250 means means that our availability drops from 90% down to 76%, and that's basically because we're restricted by weather, towing windows, further towing distance. Everything just gets that little bit harder. Um, Bottom left is the same kind of the annual productivity, kind of similar pattern to the availability. And then ultimately the LCOE on the bottom right. And again, just to highlight that these are not the absolute numbers, are not of interest here. It's the relative difference. And the using a port that's 250 kilometers away, has a significant impact on your LCOE. Um, for various reasons, less energy production and more expenditure in your OPEX and towing these wind turbines all over the place. So that's just a flavor of distance to port. Here we're varying the vessels. We use the term vessel fleet, so we don't necessarily specify how many vessels are involved in the towing of a turbine. Where we try to stay technology agnostic. So when we say vessel fleet, that might be 3 vessels, that might be just one. Um, but this, so we've talked about having 3 fleets or 5 fleets. So essentially this, in terms of turbine installation, having 5 really speeds that up. If we've only 3, that pushes it out to 4 years, which is quite the difference. Farm availability, not so much different. So obviously when we're in the kind of operations and maintenance phase, 3 vessels appears to be enough. If we have an additional 2 vessels, we only get an additional availability of less than 1%. The productivity follows that same trend. It's not a huge amount of difference. And then when we moved into levelize or the LCOE, interestingly, the having 5 fleets is actually costing us money because that actually pushes up the LCOE. So they're the kind of insights we get, and as a developer, you get to see, well, you know, how many vessels do you need? And there's probably another thing around, well, how often do you need them? Yeah, should they be assigned to the project on an annual basis or perhaps just in the summer months, etc. So that's another thing I haven't quite shown here, but it's there. The next on the left here, we just in terms of productivity, we've seen other methods of determining the annual energy production of a wind farm, and you can do simple calculations where you can determine that based on an average resource. But because we actually use hindcast data, which obviously has a variability to it, seasonally, monthly, etc. Every year is not quite the same. So I just wanted to show you here that, some years can be significantly different. So that colored column on the right is just showing you the green years are above their average, and they can be 15% above, and the red is below, and there is one that's 22% below. So it's just showing that kind of variability that exists, in annual energy production. So again, the in terms of bankability of a project, being able to kind of show that and understand that is very useful if you're the person in charge of cash flow, for example. On the right, we're looking at the sensitivity of electrical connection. So this electrical connection is connecting the electrical cable to the wind turbine when it's at site. I mean, this is also a proxy for mooring connection as well. So any connection that's made at sea. And what we're doing is we're changing the limit on what wave height that can be done in. So in the plot, we're changing it between the orange line is we can only do that when the waves are lower than 0.75 meters, and the blue line, the waves must be below 1.5 meters. And you can see that there's that affects the productivity, because any degree of taking a unit off-site and returning it, for maintenance, means that the availability is reduced because of that connection time is reducing the time the turbine is generating. And the little table at the bottom just kind of highlights, what kind of a difference there would be. So if you're somebody who's in the technology space and you're trying to say, well, we've got a technology that can essentially double the wave height that you can make this connection in. Well, we can show that essentially you can have a 25% increase in energy production if you can supply that technology. So lastly, finance. So again, I mean, this reflects maybe what I talked about earlier. So LCOE versus the number of vessels, and the port distance is the top right plot. And I guess it's fairly obvious that the greener the line is, that's the further it is from the farm. The port to the farm distance is greater. So yeah, that means that you have a higher LCOE. So you want a port that's reasonably close to the farm. Um, Slightly different when we talk about fleet numbers. So obviously, if we're far away from the farm, the more vessels we have, that top green line, the more vessels we put into the project, the lower the LCOE becomes, and that's usually because we've got more availability, we've got more energy production, so we're paying for those vessels, and they're keeping us up and running in a high production rate. The bottom blue line is actually kind of showing slightly the opposite, where if you're very close to port, if your farm is very close to port and you've got two vessels, you seem to be doing enough. Your LCOE is very low. The more vessels you put into the project, you're actually increasing your LCOE. So you're paying for vessels, but they're not adding anything in terms of energy production and thus revenue. And the last plot there is just literally again showing that kind of the blue and the green lines are your cash flow. You're obviously spending money as you go, and you've got revenue too. So yeah, that's just giving you the insight of whether you break even, or in fact, if in this example, if you don't break even. So that's it there. So if I was to, that's kind of the methodology that we've taken. So obviously, as I said, the Simray project finished. So we did have some outputs from that, and I'll just talk you through them at a high level now. I would recommend you look at the report, but just in terms of the Irish concept, and this this methodology can be applied to anywhere, at any scale as well. It could be applied to a region, or it could be that region could be anything, the Mediterranean Sea, or it could be the west coast of Portugal, whatever it is. So essentially, in an Irish context, what we found from our modelling was that in terms of the port, the onshore or in-port capacity, we'd need to have 3 full sets of components to be stored in the port prior to assembly. I would say that's at least 3. So we need them ready to go, ready to be put together. And 3 seemed to be the magic number in this, because we also found that we'd need quayside capacity for a minimum of 3 units as well, and they'd be being assembled in parallel. And then we'd also need 3 if Ireland wants to reach that goal of some 30 gigawatts of floating offshore wind by 2050, we would need 3 ports capable of that. And it's worth saying, today, again, without going into the detail, we only really have one site which is readily, let's say, convertible or upgradable into a port that's able to do this. And we don't really have the plans to change that just now. So that is something that we really need to react to quite quickly. Going back to wet storage, we really found that wet storage was a critical component. And this is, maybe we're also a victim of not having the port capacity, but essentially going back to that piece again, where as we assemble these wind turbines, we need to get them away from the quayside. And in general, in the winter months, while we're still able to assemble these turbines, we're not able to get them to site because our weather conditions are the average wave heights off the west coast of Ireland in winter can be 3 or 4 meters. So that makes towing and installation quite the challenge. So essentially, what we found in some of our simulations was if we didn't have any wet storage at all, the installation rates for a 1 gigawatt farm would exceed 8 years. And for perspective, the support schemes are tending to push that value to be 2 years. So we're way out there. So wet storage is something that really needs to be looked at in tandem with developing the ports. The other knock-on effect of weather restrictions is really, and some of those example plots hinted at it, but really what we found was that because we have quite restricted opportunities to install these wind turbines or to recover them and reinstall them during a kind of a maintenance period, to take advantage of those short and infrequent weather windows, we needed more vessels. So we needed vessels on standby that were able to react to that quite quickly. Um, so going back to DFOT, which again, I hope I haven't confused you, but DFOT is the project that we're currently running. We're in month 4 of that of 2 years now. So the next step for that is you probably will hear that we're going to disseminate some preliminary results soon. We're hoping to kind of do a bi-monthly output of the things that, our learnings as we go. We're building up to much more detailed simulations at the moment, so building on SimRay, but really looking at much more complicated models and national level models. And we're currently in the process of engaging stakeholders. So we do a lot of this through Wind Energy Ireland, who obviously have a huge membership, 200 different entities, which are, many of whom work in this space. And for us, this isn't academic research. This is industrial type research. And, that stakeholder engagement piece is very important to us. It helps us kind of identify the key risks and concerns of the industry and make sure that we're addressing those. And, the payback to the industry is that by doing that, we ensure that our results are kind of relevant and they're high impact. And that's what we want. We want our results to be used to de-risk the industry. So I would say that we anyone who's interested, you can contact me, and yeah, we're always interested to hear from people. So that's it from me. You'll find me on LinkedIn, Alan Henry on LinkedIn. So yeah, please get in touch if you want to find out more. Thanks very much.
Thanks, Alan. Yeah, what I'll do is I'll post links to both the SimRay report as well as to your LinkedIn as well, so people can find both of those things. A couple of questions for you. It was, thank you, fantastic presentation. I knew it was going to be great from our previous talks anyway. Mm-hmm. I think the first thing I want to ask is about building the national models. I mean, that's quite a complicated task, and particularly as you pointed out, when you look at like the opportunity space around Ireland, there's a bunch of like localized optimizations that I assume you have to try and do. Can you talk through maybe your methodology there and some of the challenges?
Yeah, I mean, we're probably in the thick of that at the moment, but I can give you a sense. So I guess one of the things we do, like internally, we use I use the term, I'm quite a favor of this, but I use the term port perfect. So that's the idea that you come up with a port that does what it needs to do. So it has an installation rate, or it basically has a throughput of these units that satisfies the need, at a national level. So, and then assuming that we have three of those port perfects, we can build the utopian model, if you like. And so that would probably be the first thing that we would do is build that utopian model where we have those 3 ports and they're building out, that 30 gigawatts of floating offshore wind. And then what invariably we do, and we've done in previous ones, is then we start to add restrictions, so there and those restrictions are like the weather is in there all the time, that's a default, but there's other stuff around, marine traffic in ports, tidal restrictions in ports. Some of our ports have, cruise ships will essentially own the high tide that they can get in and out of ports. So we start to, let's say, make the model more difficult. And while we're doing that, we're also varying some of these parameters. So, I think it's a really good example that the mooring connection or the electrical connection. So we can now see on a much higher level what the effect of being able to make that connection in different wave heights, what that affects on a much grander scale. Because I think, like it, I, I think the national piece is very important, because what we've seen is that many developers are talking about their project and the port that they will use, but it's going to be very apparent very quickly, if there's 3 or 4 developers who all want to use the same port, that the capacity is nowhere near there. And that competition isn't necessarily positive in terms of getting our install capacity up. So if we're thinking about that 30 gigawatts, we need to work together. And that's the port coordination piece as well. So, another kind of secondary thing is, what can smaller ports do? So are they handling all the kind of crew transfer, all the anchor handling, all the cable laying, all that kind of stuff, and understanding how that piece works as well. So
Is
yeah,
that layer,
that's our approach.
that
Yeah.
sort of, I don't know if this would be the right term, but maybe secondary ports or whatever you would call the
Yeah.
smaller ones, is that a layer that you hope to get into in future work, or is
Yeah,
that?
yeah,
Yeah.
yeah. No, that is a piece we'll do. Now we may, national level might be difficult, but there's some obvious regions in Ireland. So we did, I don't know if I included it in here, but we do have there's a kind of a map in Ireland that's often used. This one down here at the
Yeah,
bottom, it's quite
bottom, yeah,
small,
I see it.
but that's what we did in Simray. So we broke it up to the kind of northwest, the west, the southwest, and the south coast. That's floating wind in Ireland. So we had regional models. But realistically, as it stands, like, the map is quite obvious that the south coast is going to be, well, sorry, I shouldn't say that. No, the south and the west coast are going to be the first places to be developed. So focusing on them in the first instance is what we'll do. Yeah, yeah.
Okay. And then in that Simray project, earlier on in the slide deck, you were talking about the different variables, and you sort of illustrated the impact. I mean, that was where you showed that I think it was the mooring connection, for example, being able to have a 25% increase on, I think it was financial performance. But what I'm wondering is, that was an analysis of each individual variable, right? Just a sort of an isolated variable impact. Have you explored sort of the impact that might happen when you start combining some of these things, or maybe even a Monte Carlo analysis that kind of tries to optimize?
Yeah. So there is Monte Carlo analysis is built into the software, and I haven't gone down the road of presenting. You notice I haven't presented any uncertainty or anything like that. So that's all in there. And the other nice bit, as a kind of a data analyst myself, the other nice piece in the software is that you can create a study. I've presented this to you, and I've varied one variable at a time. But realistically, all these results could have come from the one simulation, because essentially we can have a multi-parameter simulation. So we vary a whole load of parameters and we get the results, and then we're able to display them. So I resisted the urge to do 3D plots or anything too confusing, but they're in there.
But essentially, it is multi-dimensional in
Oh, it
its
is
analysis.
absolutely, yeah. I mean, you can blow it up, and you can vary everything, or you can put uncertainty on everything. But the mind, 10 variables. I don't think, there's not many people out there that can handle that.
Yeah,
Yeah.
I totally understand. That ties into one of the variables, though, which was related to vessels. You talked about fleet, your terminology around
Yes, we
fleet.
use
So
fleet. Yeah.
just describe fleet again, just in case that wasn't
Yeah,
quite clear.
so I mean, maybe I think it's on the last. Yeah, there's an image on the last slide. So this image up here, top left. I'm just trying to count. So we've got a big tanker on the right. We've got the main tug, and then we've got 2 kind of guide tugs either side, and then we've got a tug aft. There's probably even a pilot vessel behind that aft tug, and there's another pilot vessel to the left as well. So, just in that picture alone, we've got 6 vessels. So I guess, we can't prescribe what each harbour master will want to see in the port, and we can't prescribe what each technology will need offshore. We try to remain technology agnostic. Now we do get engagement from technology developers and project developers who prescribe what they are using, but we try to keep our results agnostic. And so me saying that we're going to need 60 vessels of X amount of type is harder to do, because then I might be saying, well, if we use this technology or if we're coming out of this harbor. Does that make sense?
Yeah,
Like,
it
so
does.
what we're
Yeah.
basically saying is a fleet can get one of these out of the harbor. And we
Hmm.
have done simulations where we use a lot more vessels in the harbor, because Michael McCarthy from MMCC, he used to be commercial director of Port of Cork, so he knows that kind of pilotage stuff inside out. So he's been a great help with that. And then obviously as we go offshore, we wouldn't need all those vessels offshore, but we certainly need something like that when we're doing the installation too.
Yeah. So your term
So
fleet is basically that
the
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 vessels
vessel,
that are needed to
yeah,
achieve the marine operation, but you're not describing exactly how many and what
no,
type. Okay. Well,
no.
that ruins the question I was going to ask then, which is,
Okay,
but I'll mention it anyway
go for it.
because
Yeah, go for it.
one of the follow-on presentations that I'm going to be teeing up next is a phenomenal presentation from a shipbroker looking at the need for vessels to be
Okay.
getting fabricated now.
Yes.
And so the question was going to be, well, based upon your analysis, how many vessels or
Yeah.
what kinds of vessels does Ireland need? And and then I was going to ask this next presenter, like, are they in the
Yeah.
pipeline? So
No, so I think the unfortunate answer to that is that is something that we are going to look at in default. So we're trying, if we get the appropriate stakeholder engagement, we will go to that level. Um, but I think unfortunately, in answer to your question, there is a major need for vessels, and I think
mhm.
that's widely known at this point that the order books are quite long, and they don't necessarily match the targets, and that's not just an Irish issue.
No,
That's
it's
across the
much bigger.
board.
Yeah,
That's a
yeah.
much bigger problem.
The
Yeah,
presentation I saw was North Sea focused, and it talked about competition with oil
yeah,
and gas, and then
yeah,
looking
yeah.
at
So
looking at a need for a particular type of service vessel for a wind farm installation, and when it
yeah,
wasn't available, the rates essentially tripled or something
they
like that.
triple. Yeah, yeah.
Yeah.
And so to kind of to wrap that up though is what I would like to be able to say in a year to 18 months is to be able to give a kind of evidence-based result around, well, this is how many vessels we need,
Hmm.
because nobody really is talking about that. And if they are talking about it, it's more a kind of a consultant's report where you've kind of multiplied X by Y and got Z, and that's okay. But I think we see a much finer level of detail because we actually see their usage, across days and hours, which I think is a very important piece. There is a migration of vessels around the world. And if you're a vessel owner, maybe you take a trip across hemispheres every year, or you go from the Med to Ireland every year. You
Hmm.
make that migration, based on the level of work that there is. But
Yep.
but we'd like DFO to be able to somebody, vessel operators and builders, to be able to look at this and say, this is how many vessels are required. I need to get I need to
Get
either
moving.
get in that order book, or I need to start building more vessels.
I guess,
Yeah.
or the alternative though is, and in DeFi you could do this, is then just look at the cost implications, because
Mm,
when without those vessels, not only do you then have timelines that go from 2 years to 8 years
yeah.
or whatever it might be, but you also go to construction
Mm,
costs that then double and triple, and
yeah.
then
Yeah.
that has significant impact on LCOE.
Hmm. Yeah.
Yeah.
Absolutely. Yeah. Absolutely. And remember, we're speaking to developers and financiers, and if you're looking at these risks and you say 8 years to install 1 gigawatt, well, unfortunately, that project won't go ahead. It is as simple as that.
Yep.
And that will be, the support schemes, certainly in the UK, stipulate, the timeline, and if you can't fall into that, there's a huge financial risk.
Hmm.
Um, yeah. Yeah.
Yep. Excellent. Well, my last question
Okay.
was going to be about the support schemes, but you sort of identified it. So
Assumption.
yeah, it's all good. Well, this
Yeah.
is wonderful. Thank you very much, Alan, for your presentation.
No problem.
Certainly, if anybody has any questions, I'll make sure to funnel that over to you. And,
absolutely.
appreciate your time today.
Okay. No problem. Thanks, Marcus.
Cheers.